In the quiet vastness of the cosmos, some of the greatest mysteries remain unseen. Among them is dark matter, an invisible force that we cannot touch or observe directly, yet one that shapes the very structure of the universe. And then there are the dinosaurs, majestic creatures that once ruled our planet, only to vanish in a moment of cosmic violence. What could possibly link these two seemingly unrelated topics? In this journey, inspired by physicist Lisa Randall's thought-provoking ideas, we will gently explore how dark matter might have played a role in one of Earth's greatest extinctions. We will walk through the science, the theories, and the wonder behind this connection, all in a tone designed to soothe and calm. Let your mind wander through galaxies and ancient Earth alike, as we delve into a narrative where astrophysics meets paleontology, where stars and fossils tell a shared story. This is not just a story about science. It is a cosmic lullaby wrapped in curiosity. Welcome to Space for Sleep. Let us begin. Section 1. The Unseen Universe. The universe, as we perceive it, is only a fraction of what truly exists. When we look up at the night sky, we see stars, planets, and glowing galaxies. But these luminous objects make up only a small part of the cosmic puzzle. Scientists believe that nearly 85% of the matter in the universe is invisible, something we cannot see, hear, or touch. This elusive substance is what we call dark matter. It does not emit light. It does not reflect it. It passes through us, through the Earth, and through the stars themselves without interaction. And yet, its gravitational pull holds galaxies together. It sculpts the large-scale structure of the cosmos. Without dark matter, the stars would not remain in their swirling orbits. Galaxies would fall apart. The universe as we know it would simply not exist. First proposed in the early 20th century, dark matter has remained a mystery. Astronomers like Fritz Zwicky and Vera Rubin noticed that something unseen was influencing the motion of galaxies. The stars at the edges of galaxies were moving too fast, faster than expected. Something else had to be there. It wasn't just empty space. Over the decades, evidence for dark matter continued to grow, not through direct observation, but by watching how it bends light, how it affects the cosmic microwave background, and how it subtly sculpts the distribution of galaxies across the sky. We still do not know exactly what dark matter is made of. Some scientists believe it consists of undiscovered particles, perhaps WIMPs, or weakly interacting massive particles. Others suggest axions, sterile neutrinos, or even that our understanding of gravity might need to be revised. But despite this uncertainty, dark matter is one of the most important building blocks of the universe. And now, some scientists believe it may have had an effect much closer to home, on our own planet, and on life itself. Could dark matter be linked to one of Earth's most devastating extinction events? To explore this question, we must begin with the age of the dinosaurs and the mysterious end of their reign. Let us move gently through time from the darkness between the stars to the ancient Earth beneath our feet. Section 2. When giants roamed the Earth, more than 200 million years ago, Earth was a very different place. Vast forests stretched across the continents. Warm, humid climates nurtured a thriving diversity of life. And in this lush world, a group of creatures began to dominate the land, the dinosaurs. They came in all shapes and sizes, from the towering Brachiosaurus, gentle herbivores with long necks grazing from the tallest trees, to the agile Velociraptor, a quick and cunning predator no larger than a modern dog. And of course, the Tyrannosaurus rex, one of the most iconic animals ever to walk the planet. For over 160 million years, dinosaurs thrived. They adapted to different environments, survived climate shifts, and evolved into an astonishing array of forms. During this time, the continents slowly drifted apart. Oceans opened, mountain ranges rose, and entire ecosystems emerged and vanished. Life on Earth was dynamic, constantly changing, constantly evolving. But something happened. Around 66 million years ago, in an instant by geological standards, their reign came to a sudden and catastrophic end. An estimated 75% of all species on Earth disappeared, including nearly every dinosaur. Fossils provide a silent record of this moment. One layer of sediment, found in rocks all over the world, tells the tale. A thin line of iridium-rich clay, known as the KP boundary. Iridium is rare on Earth, but common in asteroids. This thin line marks the moment when a massive asteroid, roughly 10 kilometers wide, struck the Earth near what is now Chicxulub, on the Yucatan Peninsula in Mexico. The impact released energy equivalent to billions of nuclear bombs. It caused wildfires, tsunamis, a global dust cloud that blocked the sun, and a sharp drop in temperature. Photosynthesis stopped, food chains collapsed, and in the wake of this devastation, the age of the dinosaurs came to a close. But some scientists, including Lisa Randall, have asked a deeper question. Why did that asteroid hit Earth at that moment in time? Was it simply chance? Or could there be a pattern, something cosmic, guiding such events? As we continue, we will examine how dark matter might have played a hidden role in setting this cosmic tragedy in motion. A silent force, far beyond our sight, influencing life in ways we are only beginning to understand. Section 3. The cosmic clockwork. The solar system does not stand still. It moves through the galaxy, slowly, majestically, following an orbit around the center of the Milky Way. This journey takes approximately 225 to 250 million years, a single galactic year. During this time, the solar system rises and falls through the dense, disk-like plane of the galaxy, like a gentle wave passing through layers of cosmic matter. And it is here, in this rhythmic motion, that some scientists see a potential connection to the events on Earth. Lisa Randall, a theoretical physicist at Harvard University, proposes that dark matter, invisible and pervasive, might be more than a static background to this journey. She suggests that a thin disk of dark matter may exist within the Milky Way's galactic plane. This hypothetical structure would differ from the spherical halo of dark matter generally accepted by astrophysicists. Instead, it would be flatter, denser, and possibly capable of interacting, at least gravitationally, with ordinary matter. As the solar system moves up and down through the galaxy's plane, it may occasionally pass through this dark disk, and when that happens, the gravitational forces could subtly disturb the Oort cloud, a vast, distant collection of icy bodies that surrounds the solar system. These disturbances could dislodge some of those icy bodies, sending them careening inward toward the inner solar system. Some may fall harmlessly into the sun. Others, however, may be drawn toward Earth. Over millions of years, this process could explain periodic increases in impact events on Earth, like the one that ended the dinosaurs. It's a hypothesis, of course, but it invites us to see the universe not just as a distant stage for human existence, but as a deeply interconnected system where unseen forces may shape the history of life, the motion of stars, the invisible currents of dark matter, and the fragile balance of life on Earth, all parts of a cosmic dance, too vast and too slow for us to perceive directly. And yet, science allows us to glimpse this harmony, one piece at a time. In the next section, we'll explore how Lisa Randall and her team built a scientific case for the dark disk hypothesis, and how data from astronomy, geology, and paleontology might begin to come together. Section 4. A hypothesis in the shadows. Science often begins with a question. For Lisa Randall, that question was, could dark matter have played a role in one of the most dramatic extinction events on Earth? To explore this, she and her collaborators ventured into the complex terrain where cosmology, geology, and paleontology overlap. The first step was understanding dark matter, a mysterious form of matter that does not emit, absorb, or reflect light. We know it exists only because of its gravitational effects. It holds galaxies together. It shapes the large-scale structure of the cosmos. But what if dark matter isn't just sitting quietly in a spherical halo around galaxies? What if a portion of it forms a disk, a flat, thin structure within the plane of the Milky Way? This was the starting point for a new kind of investigation. A model was developed based on gravitational physics to describe what such a dark matter disk might look like. According to Randall's hypothesis, this dark disk would be dense enough to exert noticeable gravitational pull, but still invisible. As the solar system moves in its orbit around the galaxy, it periodically passes through this disk, roughly once every 30 to 35 million years. The timing of these crossings, when plotted against Earth's history, reveals something curious. They seem to correlate with periods of increased impact cratering and mass extinctions. Of course, correlation is not causation, but the alignment is suggestive. Randall's team examined data from terrestrial craters, fossil records, and sediment layers to search for patterns. They also explored data from satellite surveys that map the distribution of visible stars and gravitational anomalies. These layers of evidence, though incomplete, began to form a picture, a potential cosmic trigger linked to the mysterious behavior of dark matter. What makes this theory compelling is not just its elegance, but how it bridges the unimaginably vast galactic motion and invisible matter with the deeply intimate story of life on Earth. It reminds us that science is not just about facts, but about finding patterns and asking what they might mean. The dark disk hypothesis may never be proven definitively, but in exploring it, we push the boundaries of what it means to understand our place in the universe. In the following section, we'll journey deeper into the nature of dark matter itself, what it is, what it isn't, and how physicists are trying to uncover its secrets. One particle and one possibility at a time. Section 5. What we know and don't know about dark matter. Dark matter is among the greatest mysteries of modern physics. It does not shine, it does not glow, and it does not interact with ordinary matter in ways we can easily detect. And yet, we are sure it's there. Why? Because galaxies behave in ways that defy our understanding of gravity, unless something unseen is exerting additional pull. When the scientists measure the rotation speeds of galaxies, they find that stars near the edges move far too fast, as if held in place by invisible hands. These hands are dark matter. According to our best estimates, dark matter makes up about 85% of all matter in the universe. It outweighs ordinary or baryonic matter by more than 5 to 1. But what exactly is it? That question remains unanswered. Some theories suggest that dark matter is made up of WIMPs, weakly interacting massive particles. Others propose axions, sterile neutrinos, or even particles from unknown dimensions. What they all share is this: they barely, if at all, interact with light. This invisibility makes detection extremely difficult. Experiments buried deep underground like Xenont or Lux Zeppelin attempt to catch rare collisions between dark matter particles and atoms. So far, we've seen only hints, but no confirmation. Lisa Randall's hypothesis suggests that dark matter may not be entirely passive. Perhaps a fraction of it has the ability to interact more strongly with itself, if not with us. This interacting fraction could form structures, like the thin, dark disk we explored earlier. A hidden mirror of our own galaxy. If this is true, then dark matter is not just a background actor. It may be shaping the fate of stars, planets, and even life. Imagine something invisible yet massive moving through our galaxy, affecting the orbits of distant comets, and possibly nudging one toward Earth at just the right or wrong moment. That's the breathtaking scope of this theory. That dark matter, born in the furnace of the early universe, could play a role in the death of the dinosaurs millions of years later. In the next section, we'll revisit that moment of extinction itself, the Cretaceous-Paleogene boundary, and explore how cosmic violence reshaped the Earth forever. Section 6. The day the sky fell. 66 million years ago, Earth was thriving with life, lush forests, flowering plants, and the reign of the dinosaurs. But then, suddenly, everything changed. A massive asteroid, roughly 10 kilometers wide, slammed into what is now the Yucatan Peninsula in Mexico. The impact released energy equivalent to over 1 billion nuclear bombs, sending firestorms, shockwaves, and dust clouds around the world. It formed the now famous Chicxulub crater, a scar over 150 kilometers wide and buried beneath layers of rock. But the scar left on life was even deeper. Within a relatively short geological period, 3/4 of Earth's species vanished, including all non-avian dinosaurs. But how do we know all of this? The story comes from a thin layer of rock found in many parts of the world, called the Cape Edge boundary. This layer contains elevated levels of iridium, a rare metal on Earth's surface, but common in asteroids. It also holds shocked quartz, microscopic glass spherules, and soot, evidence of intense heat and global fires. But what brought the asteroid here? Was it pure chance? This is where Randall's hypothesis returns with new gravity. Perhaps the solar system, moving in its orbit around the Milky Way, passed through a dense dark matter disk. That passage could have perturbed distant objects in the Oort cloud, sending one on a deadly path toward Earth. In this view, dark matter doesn't just hold galaxies together. It might have nudged a space rock, triggering a global extinction event. And from that destruction, something new arose. The rise of mammals, and eventually, of us. It's a stunning idea that invisible matter, shaped by the forces of cosmic evolution, could influence the fate of creatures on a blue planet orbiting an ordinary star. In the next section, we'll dive into the mechanics of how such a galactic crossing might disturb distant orbits, and whether the pattern repeats across Earth's deep time. Section 7. Galactic crossings and cycles of catastrophe. Our solar system is not stationary. It's orbiting the center of the Milky Way at a speed of nearly 828,000 kilometers per hour. One full orbit, called a galactic year, takes about 225 to 250 million Earth years. But this orbit isn't perfectly flat. Like a boat bobbing through waves, the solar system oscillates up and down relative to the galactic plane. Roughly every 30 to 35 million years, it crosses this plane, the dense central region of the galaxy. This motion matters. If there exists a thin dark matter disk in the galactic plane, then crossing through it could exert gravitational forces, tugging on distant objects in the solar system. Picture the Oort cloud, a vast spherical shell of icy bodies that encircles our solar system at great distances. These frozen remnants are sensitive to even the slightest nudge. A gravitational disturbance, like from a dense band of dark matter, might dislodge some of these comets, sending them tumbling inward toward the Sun, and occasionally toward Earth. Lisa Randall and her colleagues explored whether there's a pattern in Earth's history, a cycle of mass extinctions or impact events occurring roughly every 30 to 35 million years. Some data seem to support this idea. A periodic increase in cratering events, extinction levels, or major biological transitions. If dark matter is involved, then it isn't just shaping galaxies on the grandest scales. It may also be acting as a cosmic metronome, setting the rhythm of catastrophe and renewal on Earth. Of course, much remains unproven. The exact structure of dark matter and whether a dense disk truly exists is still under investigation. But the elegance of the theory lies in its ability to link distant realms, the behavior of unseen particles in space, to the fragile thread of life on our planet. In the next section, we'll look deeper at the evidence for this cycle and explore the techniques scientists use to read Earth's ancient memory, locked within rocks, fossils, and craters. Section 8, Reading Earth's Memory. The fossil record and impact clues. Earth keeps a quiet but enduring record of its past. Layer upon layer, its rocks and sediments archive moments of drama, silence, birth, and extinction. These layers, studied in stratigraphy, are like pages of a geological book, and scientists have learned to read them. Within these strata lie the fossilized remains of creatures long gone. The abrupt disappearance of certain species in specific layers tells us that mass extinctions occurred. But how do we connect those extinctions to possible cosmic events? One method is identifying impact signatures. For example, the KPG boundary layer, found in sediment cores and rock outcrops around the world, contains high concentrations of iridium-shocked quartz, which only forms under extreme pressure. Microtectites, tiny glass spheres created by molten rock thrown into the atmosphere. These indicators suggest not just death, but an impact, a violent collision from space. But can we find evidence for repeated patterns? Could extinction and impact events occur on a roughly 30 million year cycle? Some studies suggest yes. Researchers have compiled databases of crater ages and extinction markers, then performed statistical analyses to search for periodicity. Though the data is noisy and incomplete, a signal may be there, a faint but persistent beat in Earth's history. This aligns intriguingly with the solar system's vertical oscillation through the galactic plane. And if a dark matter disk exists, its gravitational pull might be the trigger for these regular upheavals. Imagine Earth as a fragile globe traveling through the galaxy, passing every few tens of millions of years through an invisible band that could spell doom. These periodic passages could explain not just the dinosaur extinction, but other mass die-offs, such as the late Devonian or the Triassic-Jurassic events. Still, the case is not closed. More data, more impact craters, more fossil analyses are needed to confirm or reject this pattern. Yet even with uncertainty, the idea is poetic. that deep time, extinction, and rebirth might be woven into the very fabric of our cosmic journey. In the next section, we'll explore the physics of dark matter in more detail and ask why, despite its profound influence, we've never seen it directly. Section 9, the invisible thread. What is dark matter, really? Dark matter is not just mysterious. It is the most dominant form of matter in the universe, yet we don't know what it's made of. Unlike the atoms that build stars, planets, and life, dark matter doesn't emit, reflect, or absorb light. It doesn't interact with electromagnetic forces, which means telescopes can't see it. So how do we know it exists? The answer lies in gravity. Galaxies rotate at speeds that, based on visible matter alone, should tear them apart. Yet they stay intact, suggesting there's extra mass holding them together. That unseen mass is what we call dark matter. It also bends light through a phenomenon known as gravitational lensing. Light from distant galaxies curves as it passes through invisible structures, again pointing to the presence of something we cannot see. But what is it made of? That's one of the biggest questions in physics. Many scientists believe dark matter is composed of WIMPs, weakly interacting massive particles. Others propose axions, ultralight particles with strange properties. More recently, some theories suggest a dark sector, where dark matter might be as rich and complex as the visible world, with its own forces and interactions. But to date, no dark matter particle has ever been detected directly. Experiments deep underground try to catch a glimpse. Telescopes scan the sky for unusual gamma rays. Particle accelerators attempt to create dark matter in collisions. So far, the results have been elusive. And yet, without dark matter, the universe as we know it wouldn't exist. Galaxies wouldn't form. Stars might not cluster. The large-scale structure of the cosmos would be vastly different. It's as though the visible universe is just a small island in a much larger, unseen ocean. And perhaps every few million years that ocean stirs, gently shaking the island, rewriting the story of life. In the next section, we'll explore how Lisa Randall connects these cosmic truths with the fragile fate of species like the dinosaurs, and how this bridge between physics and paleontology could change our understanding of extinction. Section 10, Bridging Worlds, Physics Meets Paleontology. At first glance, dark matter and dinosaurs seem like ideas from different worlds. One belongs to the realm of particle physics and cosmology, the other to biology and ancient Earth. But Lisa Randall saw something more, a possible connection woven through time. She proposed that dark matter is not just a silent player in galactic evolution, but may have helped shape life's history on Earth. Her idea began with a question. What if our solar system regularly passes through a dense disk of dark matter? If such a disk exists, thin, massive, and unseen, its gravitational tug could slightly disturb the Oort cloud, the distant shell of icy bodies that surrounds our solar system. These disturbances might send a shower of comets toward the inner solar system, dramatically increasing the chances of impact events, like the one that ended the age of dinosaurs. It's a theory that unites galactic dynamics with mass extinctions. Randall collaborated with astronomers and geophysicists to test the idea. Together, they analyzed crater ages, extinction records, and the solar system's oscillation cycle. Their conclusion: the data doesn't prove the theory, but it's plausible, consistent with what we know, and testable with future discoveries. More importantly, it opens a new way of thinking, that events far beyond our planet can shape the evolution of life here. the dinosaurs didn't just lose a game of chance with an asteroid. They may have been part of a much larger cosmic rhythm, a pattern governed by the structure of the Milky Way itself. Such ideas remind us that science is often about asking the right questions, even when the answers are not yet clear. In the next section, we'll step deeper into the evidence, the data, the numbers, and the cosmic cycles that might tie dark matter to Earth's biological history. Section 11. Cosmic Cycles and Crater Clues. If dark matter really plays a role in shaping life on Earth, the evidence should be etched in stone, literally. That's why scientists look to crater data and extinction timelines, searching for repeating patterns that span millions of years. The Earth's surface is constantly reshaped by erosion, plate tectonics, and vegetation. Yet some craters survive the march of time, silent scars that record past cosmic encounters. One of the biggest is the Chicxulub crater, buried beneath Mexico's Yucatan Peninsula. It marks the impact that likely ended the reign of the dinosaurs, roughly 66 million years ago. But is there a pattern to such catastrophic events? Some researchers have proposed that mass extinctions occur in cycles every 26 to 30 million years. Others suggest the impact rate of large comets and asteroids rises periodically. If that's true, what could be driving this rhythm? Lisa Randall's hypothesis is one possibility, that the solar system oscillates above and below the galactic plane, completing a full cycle roughly every 64 million years, and that during each pass through a dense dark matter disk, gravitational forces stir the Oort cloud, sending cometary debris toward the inner planets. This movement is not fast, it's slow, almost imperceptible, like a cosmic pendulum swinging across the eons. Still, the theory depends on the existence of such a dark disk, and that remains unconfirmed. Astronomers continue to search for subtle gravitational effects that might reveal its presence. They also refine the ages of impact craters using radiometric dating and compare extinction events with galactic models. While no single piece of evidence is conclusive, the emerging picture is one of interconnection, that the universe's largest structures may ripple down to affect even the smallest creatures on Earth. In the next section, we'll explore the tools and technology scientists are using today to probe the invisible. From underground detectors to space-based observatories. Section 12, The Invisible Hunt. Detecting dark matter. Dark matter, by its very nature, does not shine. It does not glow, reflect, or emit radiation. And yet, scientists are building some of the most sensitive instruments on Earth in hopes of catching the faintest whisper of its presence. The search for dark matter has become one of the most ambitious quests in modern physics. In deep underground laboratories, shielded from cosmic rays and background noise, massive detectors wait in silence. One such effort is the Xenon experiment, buried beneath the Gran Sasso Mountains in Italy. Here, tanks of liquid xenon sit in darkness, ready to record the tiniest flashes of light caused by a potential dark matter particle bumping into an atomic nucleus. These particles, if they exist, are thought to be WIMPs, weakly interacting massive particles. Lisa Randall, however, is among those exploring alternative possibilities. She suggests that dark matter may not consist of just one kind of particle, but could be more complex, perhaps forming its own version of atoms, or even a dark disk within the Milky Way. To investigate these ideas, scientists use not only ground-based detectors, but also space telescopes and particle accelerators. The Large Hadron Collider at CERN smashes protons together at near-light speeds, hoping to generate exotic particles, some of which might hint at the presence of dark matter. Meanwhile, satellites like Fermi observe high-energy cosmic events, looking for indirect signals, such as excess gamma rays that could arise from dark matter annihilations. It's a bit like trying to find an animal in the forest, not by seeing it directly, but by observing broken twigs, fading footprints, and distant rustlings in the leaves. Despite decades of searching, dark matter remains elusive, but each non-detection helps refine the theories, ruling out what dark matter isn't, and sharpening our sense of what it could be. These investigations stretch the boundaries of what we can measure, and they remind us that progress in science often lies not in certainty, but in the courage to explore the unknown. In the next section, we'll delve into how dark matter may shape not just galactic structure, but the behavior of galaxies themselves, setting the stage for the cosmic web in which all things, including Earth, are suspended. Section 13, Sculpting the Cosmos, Dark Matter and Galactic Form. When we look at galaxies through a telescope, we see luminous spirals, glowing cores, and dancing stars. But hidden behind this celestial choreography is an unseen hand, dark matter, shaping every move. Galaxies are not held together by visible matter alone. In fact, if we calculate the mass of all the stars, gas, and dust we can see, it accounts for only a small fraction of the gravitational pull observed. Something invisible must be holding them together. That something is what scientists believe to be dark matter halos. Vast spherical regions of unseen mass surrounding every galaxy. These halos provide the scaffolding upon which galaxies are built, dictating their rotation speeds, their shapes, and even their stability. Lisa Randall emphasizes that dark matter is not just a background player. It is fundamental to the very architecture of the universe. The patterns we observe in the cosmic web, an immense network of filaments stretching across the cosmos, are guided by the invisible gravitational framework dark matter provides. Without it, galaxies would likely have never formed. Stars might not have clustered. Planets, and perhaps life itself, might never have emerged. Scientists observe this by looking at the rotation curves of galaxies. According to Newtonian physics, stars farther from a galaxy's center should orbit more slowly, but they don't. They move at nearly constant speeds, a clue that something massive but unseen surrounds them. Dark matter's influence is not limited to the present day. It played a crucial role in the early universe, helping to seed the first galaxies by drawing in ordinary matter through gravitational attraction. As clusters formed and grew, so too did the complexity of cosmic structures. In this way, dark matter is not just a mystery to be solved. It is a cosmic artist, painting the grand design of the universe. And if Randall's ideas are correct, its brushstrokes may have reached all the way down to Earth, guiding not just star systems, but also the fate of the creatures that walked its surface. In the next section, we'll look more closely at the intersection of cosmology and paleontology, and how seemingly unrelated sciences can converge in surprising ways to reveal a fuller picture of reality. Section 14, Bridging Worlds, Cosmology meets Paleontology. At first glance, the universe of stars and the world of dinosaurs may seem galaxies apart, one concerned with celestial motions, the other with ancient bones. Yet, in Lisa Randall's view, these fields are intertwined, connected by forces that operate across unimaginable scales. The extinction event that ended the age of dinosaurs is typically attributed to an asteroid, but the why now question remains. Why did such an impact occur at that particular moment in Earth's history? This question opens a door, a path leading from paleontology to planetary motion, and ultimately to the structure of the galaxy itself. Randall proposes a bold idea, that a disk of dark matter, thinner and denser than previously imagined, exists in the plane of the Milky Way. As our solar system orbits the galactic center every 250 million years, it oscillates up and down through the galactic plane. Roughly every 30 to 35 million years, the Sun, and all of us along with it, pass through this midplane. If a dense dark matter disk exists there, its gravitational effect could disturb the Oort cloud, a distant reservoir of icy bodies surrounding the solar system. These disturbances might send comets inward, occasionally causing impacts on Earth. And if those impacts coincide with the mass extinctions, we begin to see a deeper pattern, one where cosmic cycles influence life on our planet. It's a hypothesis still being tested. It requires more evidence, not only of the dark matter disk's existence, but of a reliable correlation between galactic oscillations and extinction events. Yet the value of the idea is in its interdisciplinary reach. It invites paleontologists, physicists, astronomers, and geologists to work together on a puzzle that spans both time and space. The asteroid may have ended the dinosaurs, but dark matter may have whispered its approach. In the next section, we'll delve deeper into the Oort cloud itself, a mysterious and distant frontier where comets are born and where Randall's theory takes physical shape. Section 15. The Oort cloud, a distant reservoir of cosmic change. Far beyond the planets, past the frozen reaches of Neptune and Pluto, lies a realm almost entirely invisible, the Oort cloud. This vast spherical shell surrounds the solar system, extending perhaps a light year from the Sun. It's not composed of stars or planets, but of billions of icy bodies, ancient relics from the formation of our solar system. These fragments of rock and frozen gas are mostly dormant, orbiting silently in deep space. Yet from time to time, something disturbs their slumber. A passing star, a molecular cloud, or perhaps, as Lisa Randall suggests, the gravitational influence of a dense disk of dark matter. When this happens, some of these icy bodies are knocked from their distant orbits and sent hurtling inward toward the inner solar system. As they approach the Sun, they begin to warm and glow, becoming the comets we observe from Earth, long glowing tails trailing behind them. But some of these comets may do more than just dazzle. Occasionally, one collides with a planet, and in the case of Earth, such an impact can change the course of history. The theory Randall proposes is elegant. If the Sun's oscillation through the galactic plane periodically disturbs the Oort cloud, then those disturbances may align with known extinction cycles. This idea links a distant icy cloud to one of the most dramatic events in Earth's history, the mass extinction that ended the reign of the dinosaurs. Though the theory remains under investigation, its beauty lies in the way it connects the very small, icy fragments far from the Sun with the very large, the gravitational structure of the Milky Way. It's a reminder that even the most distant and cold corners of space may hold the keys to understanding life and death on Earth. In the next section, we'll look more closely at the asteroid impact itself, the scientific evidence we've gathered, and what it tells us about the day the dinosaurs vanished. Section 16, the day the sky fell, uncovering the asteroid impact. Around 66 million years ago, a single moment changed the course of life on Earth. The skies darkened, the air thickened with ash, Oceans surged, forests burned, and the age of dinosaurs came to an end. Scientists now agree that this dramatic shift was caused by a massive asteroid or comet colliding with Earth near what is now the Yucatan Peninsula in Mexico. The evidence lies beneath the surface, a vast buried structure known as the Chicxulub crater, over 180 kilometers wide. Discovered in the late 20th century, this crater has become a crucial piece in the puzzle of the Cretaceous-Paleogene extinction event. Around the world, geologists have also found a thin layer of sediment, rich in iridium, a rare element more common in asteroids than in Earth's crust. This layer, known as the K-peak boundary, marks the end of the Mesozoic era and the beginning of the Cenozoic. Beneath this layer, fossils of dinosaurs and many marine species abound. Above it, they are gone. The impact would have released energy equivalent to billions of atomic bombs. Shockwaves, wildfires, tsunamis, and a nuclear winter-like effect likely followed, blocking sunlight, collapsing ecosystems, and driving a catastrophic loss of life. But what if the asteroid's journey from the edge of the solar system to Earth was triggered by an unseen force? Lisa Randall's theory of a dark matter disk doesn't contradict the impact hypothesis. It extends it. The impact happened. The crater is real. But the reason why such an object arrived at that particular time may be written not just in Earth's geology, but in the movements of stars, planets, and invisible matter. The story of the Chicxulub impact is a story of cause and consequence, and Randall invites us to explore those causes at a cosmic level. In the next section, we'll explore the aftermath, how ecosystems reshaped, new life forms emerged, and mammals, including our distant ancestors, rose to fill the void left by the giants. Section 17. After the impact, rebirth from ashes. In the aftermath of destruction, Earth was silent. The asteroid's impact had plunged the planet into a dark, frigid state. Sunlight was blocked by dust and aerosols. Photosynthesis stalled, and the food chain collapsed. Yet from this devastation, a new chapter began. The age of dinosaurs had ended, but life, resilient and persistent, began to reclaim the Earth. In the oceans, plankton slowly returned, forming the base of the marine ecosystem once again. On land, small mammals, who had lived in the shadows of dinosaurs, began to flourish. Their size, burrowing habits, and adaptability made them well suited to the harsh conditions. Over millions of years, these humble survivors gave rise to an astonishing diversity of mammals, including eventually primates and humans. The landscape of Earth transformed. Forests regrew. New species evolved. The Cenozoic era, often called the Age of Mammals, had begun. Birds, descendants of certain dinosaurs, also survived and diversified, filling ecological niches once held by pterosaurs and other ancient flyers. Life had not been erased, only rewritten. Lisa Randall reflects on this transformation as a powerful reminder of nature's cycles. Destruction often precedes creation. And while dark matter may have been the catalyst, it was Earth's own biology that wrote the next chapter. It's humbling to consider that the space beyond our atmosphere and the forces we cannot see might shape the very path of evolution. In the next section, we'll step back and examine the broader implications. How does this understanding change the way we view our place in the cosmos? Section 18. Our place in a cosmic web. When we gaze up at the stars, we often wonder where we fit in. Are we merely observers, or are we participants in a larger cosmic story? Lisa Randall's exploration of dark matter invites us to see Earth not as isolated, but as part of a dynamic cosmic ecosystem. The theory that a thin disk of dark matter may periodically disturb comets in the outer reaches of the solar system forces us to consider how interconnected we are with the invisible universe. The extinction event that wiped out the dinosaurs was not merely an earthly disaster. It may have had a cosmic cause. That realization reframes our sense of scale. We often think of evolution, geology, and biology as terrestrial processes. But the deeper truth is this: space and time shape life itself. The gravitational pull of stars, the motion of the galaxy, the silent presence of dark matter. All of these may influence what lives and what dies on this planet. We are bound into a cosmic choreography, our fate entwined with the structure of the universe. In this view, the extinction of the dinosaurs wasn't just the end of one chapter. It was the beginning of another, one that led to mammals, to primates, to the development of thought, language, and curiosity. And now, to you, listening to the story of how dark matter may have shaped that path. Randall's work reminds us that the universe is not merely out there separate and cold. It is part of us. The atoms in our bodies, the rhythm of our years, the trajectory of our past, they all trace lines through the stars. In the next section, we'll explore what this knowledge means for science and how it could guide future discovery.
Section 19, Looking Forward, Science Beyond the Horizon. With each scientific discovery, we peel back another layer of mystery. Lisa Randall's dark matter hypothesis has not only redefined our understanding of mass and motion in the universe, it has also expanded the frontiers of what science dares to imagine. Her idea that a dark disk within the Milky Way could trigger comet showers and ultimately mass extinctions may be bold, but it is also testable. It inspires new directions for astrophysics and planetary science. One of the most exciting aspects of her work is that it urges collaboration between disciplines. Cosmology, geology, paleontology, and particle physics all must work together to piece together the puzzle. Future telescopes and space missions may one day detect the elusive signals of this hypothesized dark matter disk. Or perhaps particle accelerators on Earth will catch a fleeting glimpse of a dark matter particle as it whispers through detectors. But beyond data and theories, there is something profoundly human in this quest, a desire to understand not just how the universe works, but how it shaped our own history. The very forces that sculpted galaxies may also have steered the fate of species, opened evolutionary doors, and led to consciousness itself. If dark matter played a role in clearing the stage for mammals, then we owe our existence in part to the quiet influence of the invisible cosmos. The next generation of scientists may confirm or challenge Randall's ideas, but either way, the conversation she began will echo through classrooms, observatories, and imagination for years to come. In the final section, we will reflect on what this journey has revealed, not only about dark matter and dinosaurs, but about the nature of curiosity itself. Section 20, Reflections in the Darkness. As we reach the end of this journey, we find ourselves in a place of quiet wonder. We have traveled across billions of years, through stellar nurseries and ancient oceans, alongside vanished giants and the ghostly trails of comets. And through it all, we have followed a single thread: the idea that dark matter, this mysterious, unseen substance, may have helped shape the history of life itself. Lisa Randall's vision is more than a hypothesis. It is an invitation to see the cosmos not as a distant spectacle, but as a living system of which we are a part. In this story, extinction and emergence are not separate from the stars, but intertwined with them. Dinosaurs once ruled the earth, massive, powerful, majestic. Their end was sudden, but perhaps not random. If dark matter was the unseen hand tipping the cosmic balance, then the universe itself helped clear the way for mammals to rise, for minds to awaken, for questions to be asked. And now, here we are, wondering, listening, seeking. darkness that surrounds us is not empty. It holds answers we've only just begun to hear. It connects the fall of an asteroid to the arc of a galaxy, the birth of a planet to the collapse of a star. In understanding that connection, we glimpse a greater truth, that the universe is not indifferent, it is interwoven with life. And even in its darkest corners, there is meaning. So as you close your eyes or simply reflect, let this story linger. A gentle reminder that in the vastness of space, you are part of something extraordinary.